All right, the fun continues. Previously we looked at vector equations of lines. Now we're going to look at intersections of lines and skew lines. So this is lecture 26 of VC Specialist Maths Units 3 and 4. So some of the prior knowledge for this is going to be quite detailed. So you need to have watched these videos or at least have an understanding of these concepts: introduction to vectors, kinds of lines in 3D space, resolving vectors into rectangular components, what the dot product is, and importantly for this video, vector equations of lines, because in the previous video we spoke about how we can define a line in space using a vector equation, and now we're going to start talking about what it's like for two lines to intersect or to be parallel or to be coincident and that sort of stuff. So the key concepts we'll cover here are coincident lines in 2D, parallel but distinct lines in 2Ds, intersecting lines in 2D, and then we'll look at coincident slash parallel lines in 3D, skew lines in 3D, intersecting lines in 3D, and then the angle between two lines. It's getting quite heavy, the content now. So as usual, I'll put timestamps on the video if you just want to pause it and maybe just read it. That might be a good idea because I'm going to try and explain it, but it gets hard after a while because it gets pretty technical. So let's jump into it. The first thing we're going to look at is coincident lines in 2D. So just reminding ourselves of what we would have learned, hopefully in methods, unit 1 and 2. If you've got in two-dimensional space, you can have three situations. The lines can be coincident, which just means they're on top of each other. Lines can be parallel, or they can intersect at one point. So the first example we're going to look at is when we've got coincident lines in two dimensions. But obviously here we're defining it using a vector equation. Okay, so just a bit of a recap. We're going to call it line one. Line one is going to be in blue, and we're going to say, all right, that's defined by the vector equation R1 of lambda, which is equal to I plus 2j plus lambda by 2i minus j. Now, just remembering this part here is kind of the direction vector. That's telling you the direction in which your vector is traveling, and then this is sort of a point that's on the line, and lambda is obviously a real number. Similarly, we've got line 2 in red, which is R2 of mu, which equals 3i plus j plus mu multiplied by 2i minus j, where mu is a real number. Now, the first thing we want to recognize, and this again is prior knowledge from the previous video, is that 2i minus j are the direction vectors of these, and they are the same. So the lines are parallel. Now, the question is, you can have lines in two-dimensional space being parallel, or can be coincident. In both cases, they're parallel. So what we need to do here is to check if they coincide. So we're going to test if 3i plus j, which is, remember, we know that 3i plus j is a point that's on line 2. We need to check if it is on line 1. And so the way we're going to do that is we're going to take line 1, which is I plus 2j plus lambda by 2i minus j. We're going to ask ourselves the question, is there some lambda such that when we equate the coefficients, we get the same lambda? So that's why we have a question mark over this equal sign. We're saying, all right, is there some value of lambda such that the x component and the y component, aka the coefficients of I and j, are equal to one another? So what we do is we equate the components. So we say the I component is 1 plus 2 lambda. Okay, so looking at this, if we expand the lambda in, we get 2 lambda I plus I. Take the I out as a factor. The coefficient of I is 1 plus 2 lambda. And we know that we know that a point on L1 is 3i. So we need to see that these equate. Okay, and then we get a j component is 2 minus lambda equal to 1. Okay, solving these equations, we get both equations give the same value of lambda. We can see that if we solve these for lambda, we get 1. So the point lies on R1, so L1 and L2 are coincident. So we knew straight away that they were parallel, but now we can say, because we know that there is a lambda such that R1 hits the point that's on um, R2. So we know that they're coincident. Okay, here's a diagram to sort of see. This is the line that R1 traces out in blue. And you'll see that when we trace out R2 now by changing mu, you can see that they're coincident. Okay. And maybe just to really drive home the fact, we knew that the point we were interested in was 3i plus j, so that's going to be the coordinate 3, 1. So 3, 1 would be there, I think. Let me get that right. Yeah, so we can see this black dot here is at the point 3, 1 now, and we can see that both those lines obviously go through that point 3, 1. That's sort of the point that we checked. We didn't have to check that point, but it was just that point was sort of obvious that it was on L2, 3i plus j. So hopefully that's making a bit of sense. So that's coincident lines in two dimensions. All right, next thing we're going to look at is, if it would load, we're going to look at parallel but distinct lines in 2D. Okay, so again, we get given line 1, which is 2i plus 2j plus lambda by I minus j. And R2 is 2i plus 3j plus mu by 2i minus 2j. Okay, we can see that the direction vectors are parallel. Okay, I minus j would give us a rise over run of -1. Okay, so similarly here, -2 divided by 2 is -1, and up here, -1 divided by 1 is -1. So the gradient of this line is -1. So we know the direction vectors are parallel. Okay, now we need to check if they coincide. So we're going to test if 2i plus 3j, which is a point on L2, lies on L1. So we're going to set line 1, or R1, the vector R1, the vector equation R1 equal to 2i plus 3j, and then work out if there is a lambda such that the I components and the j components are equivalent. So again, R1 of lambda equals 2i plus 2j plus lambda by I minus j. We're going to ask the question, is that ever equal to 2i plus 3j? Because if it is, then they're coincident. And if it's not, then they're not coincident. They must be parallel but distinct. So equating the components, we get 2 plus lambda equals 2, equating the coefficients of the I components, and then the j components, 2 minus lambda equals 3. Solving them, we get lambda equals 0 or lambda equals -1. So we can see that these two equations give contradictory values for lambda, 0 and -1, so no single lambda exists. And our conclusion, therefore, is that the point does not lie on L1. So L1 and L2 are parallel because the direction vectors are parallel, but they are distinct. Okay, so again, tracing this out, that's our blue line. This time they will not coincide, but they will be parallel. Okay, and sure enough, you get that situation. That's the lines that R1 and R2 trace out. Okay, so that's parallel with distinct lines in 2D. Next thing we're going to look at is intersecting lines in 2D. Okay, so obviously in two dimensions, if they're not parallel, then they're going to cross at some point. So maybe pause the video and just have a read of this, but I might make that smaller in case that's covering it. Okay, intersecting lines in 2D. So again, we get given two vector equations, R1 and R2. The direction vectors are not parallel. So 2i minus j and I plus 2j are not parallel. So the lines may intersect at a point. Okay, the reason we say may is because we could be thinking about this in 3 dimensions, but in this case it's 2 dimensions, so they will intersect if they're not parallel. In any case, what we're going to do is we're going to equate the two lines, okay? Because just like you'd be used to with linear relations, if you need to find the intersection between 2 points, you just set them equal to each other. So let R1 of lambda equal R2 of mu. And so we're just setting this equal to this. Okay, and equate the components. So we're going to get I plus 2 lambda equals 3 plus mu. So that's equating the I components. And then just rearranging and simplifying a little bit, you get 2 lambda minus mu equals 2. Okay, similarly, the j components, equate them. Again, just how I'm getting that idea, 2 minus lambda. Well, that's the 2 here. Lambda multiplied by negative j is negative lambda j. So you take j out as a factor, you're left with the coefficient of j being 2 minus lambda. Okay. And it equals -1 plus 2 mu. And so you get negative lambda minus 2 mu equals -3. Okay, now you've got two simultaneous equations, equation 1 and equation 2. Solving them simultaneously, I suspect if you're doing this, you know how to do that. You'll get lambda equals 7/5. Okay, substitute lambda equals 7/5 into mu equals 2 lambda minus 2. So we're substituting lambda equals 7/5 to find what mu is. Mu turns out to be 4/5. Okay, that's not probably super necessary to find the answer, but yeah, it's just good to know what mu is in any case. So what we're going to do, find the intersection point by substituting lambda equals 7/5 into R1. So we substitute that into R1 because we know what lambda is. We know what lambda is where they intersect. So we substitute that in, you get 19 on 5i plus 3 on 5j, just substituting in 7/5 into R1. And so, yeah, we get that the lines intersect at this point here, 19 on 5i plus 3 on 5j, which is this coordinate here. And sure enough, we change the values of lambda. We get something like that, and then we change that. You notice that they intersect at that point. I think that's pretty cool. And yeah, that is how you find where two vector equations intersect in 2 dimensions. Yeah, you just set them equal to each other and then crunch the numbers. Hopefully that is making a bit of sense. What we're going to do now is we're going to move into 3 dimensions. So let's try that. Okay, so the first thing we're going to do is look at coincident/parallel lines in 3D. I'm not going to do both. We'll just look at an example of coincident lines, but the same idea holds true for parallel lines in 3D. So let's have a read. We can determine whether two lines in 3 dimensions are coincident or parallel by similar methods as in 2 dimensions. Okay, so pretty much doing the same thing as we did before. We just got an extra dimension to worry about. So consider two lines L1, which equals R1 of lambda equals A1 plus lambda by D1, and L2 equals R2 of mu equals A2 plus mu D2. Okay, this is the key point. Lines L1 and L2 are parallel if and only if the direction vectors D1 and D2 are parallel. Okay, i.e. D1 equals D2 for some real number M. Okay. That just means, yeah, don't stress too much about that. It just means if D1 equals D2, then they're parallel. Okay. If lines L1 and L2 are parallel, then we can check whether they coincide by checking whether a point on L1, such as a point with position vector A1, lies on L2. So it's basically what we did before. If they're parallel, we need to check if they coincide by checking if, by checking if there's a point on L1 that's also on L2. Okay, so let's look at an example of coincident lines here. So R1 is this, R2 is this. Okay, look at the direction vectors, 2i minus j plus 4k, 2i minus j plus 4k. These are parallel. So we know that they're parallel, so the lines are either coincident or they're parallel and distinct. What we're going to do here is prove that they're coincident. So what we're going to do is set them equal to each other and then equate the components. When you equate the components, you'll notice that the solution for lambda is 1 for all 3 equations, so the lines are coincident. Okay, because there is a lambda that will, the lambda is the same for all of them. So yeah, you've got a situation where the lines coincide. And just so you know, so sort of R1 is in orange here, if I had to pick different colors. R1 is in orange. It traces out this line in 3D space. So you can get a feel for it. There it is. And so the pink line as well. It would let me move it. It's a bit slow because there's so much information. But there you go. There you can see that the lines are coincident. They're on top of each other. Okay, so again, using the same method we did in 2 dimensions, um, yeah, we can show that the lines are coincident. Okay, next one. Skew lines. Okay, so again, you're going to need to know a little bit about what a skew line is. A skew line is a unique case in three dimensions where the lines aren't parallel, but they don't intersect. So you can see here, just to get an idea of what that idea is, trace this pink and this orange one out already. Skew lines, clearly see that they're not parallel, but they also don't intersect, which can only happen in three dimensions, or maybe in higher dimensions, but certainly can't happen in two dimensions. Okay, so let's look at this example. Show that the following two lines are skew lines. Well, we've got this line here and this line here. I trust you can have a read of that. All right, first note that the lines are not parallel. Okay, I minus j plus 2k does not give us the same gradient as 2i plus j plus k. The direction vectors are different. Okay, which is what this says. Um, yeah, there is no m such that these are the same. That's basically saying, yeah, I can't scale up or down the direction vectors such that they would give us the same gradient. And that's what this symbol here means for all m, element of real numbers. This doesn't hold true. There's no m that would work. Okay, so to determine if the lines intersect, we equate R1 equal to R2. And so set them equal to each other, equate the coefficients, equate the components. So I trust that you can have a read of that. Solve the simultaneous equations. You'll get lambda equals negative 1/3. Similar to before, substitute negative 1/3 into mu to find mu. So mu is negative 2/3. Okay, then what you're going to do is you're going to check it with equation 2. So what you did here is from equation 1 and equation 3, we got lambda and mu. Okay, then we need to cross-reference it essentially with equation 2 to see if it holds true. So substituting those values into equation 2, we get that the left-hand side is 10 on 3, but we get the right-hand side is 1/3. They're clearly not equal to each other. So the lines do not intersect, and we know that they're not parallel. Okay, so since the equations are inconsistent, there are no values of lambda and mu such that R1 of lambda equals R2 of mu. Therefore, the two lines are skew as they are not parallel. We know that from the direction vectors, and they do not intersect. Okay, because if they did intersect, there would be values of lambda and mu. There'd be values of lambda and mu where all three coefficients of I, j, and k are component vectors that would equal that at some point, right? So yeah, we can see that these lines are skew, and then we've shown that they're skew lines. Okay, and obviously lambda and mu, just tracing out those lines. And yeah, how cool is that? Pretty nifty, huh? Having as much fun as I am, hopefully. So look, next one, intersecting lines in 3D. Okay, so maybe I'll hide that for now. Okay, so lines in three-dimensional space. So find the point of intersection of these lines. So again, we've got two vector equations of lines. At the point of intersection, we know that um, R1 of lambda equals R2 of mu because they have to be equal. Okay, we're doing the same thing we did before. We're going to equate the coefficients of I, j, and k. So from 1 and 2, we get 7 plus 3 lambda equals 1. So lambda equals negative 2. Substitute that into one of the other equations. We get mu equals 4. Okay, and then we check it with the other equation that we didn't use. So we verify with equation 3 in this case that 6 minus 2 times 4 equals negative 2, which is the correct value of lambda. So those values match up. So the point of intersection is when lambda is negative 2. So when lambda is negative 2, we can see that that black point there is the point of intersection. Yeah, by substituting a negative 2 into R1, you get I minus 2k. And so thus the lines of intersection are, the point of intersection is at 1, 0, negative 2. So if I change the pink vector now as well, when the pink vector is mu has to be 4. So you can see that that's the point where they intersect. Let me get there. And so yeah, there's our lines. That black point is the point 1, 0, -2. So I think that's pretty nifty. Let's just trace out the lines a bit more so we can see what we're doing. And yeah, that's what it's all about. Thrilling stuff. All right. Cool. All right. Let's have a look at the last thing, I think. Yep. Which is angle between two lines. All right. So here's the theory. Given two vector equations, R1 and R2, defined just like we've been defining them, A1 plus lambda by D1, and R2 is A2 plus mu by D2. The angle theta between the direction vectors is given by this. Cosine of theta equals D1 dotted with D2 over the magnitude of D1 multiplied by the magnitude of D2. And remember that if the dot product between D1 and D2 is 0, then the lines are perpendicular. Okay, remember the dot product is a measure of how much two vectors are pointing in the same direction. If the vectors are not at all pointing in the same direction, then they're perpendicular. So the dot product will be equal to 0. Okay, this obviously isn't a proof. I'm sure the proof isn't too tricky, but something to think about why this is the case. I think it's just an application of the dot product. Anyway, I'll have a think about that. Let me know what you think. Okay, but here's just an example. D1 is 2i plus 3j plus k, and D2 is I minus j plus 4k. Okay, notice that the only thing we need in order to determine the angle between the vectors is the direction vectors, right? We don't really care necessarily where it's pointed in space. We just need to know where which direction the vectors are pointing in, because then we can just find the angle between them, right? So compute the dot product gives us 3. The magnitude of D1 and D2 is the square root of 14 and the square root of 18 respectively. Cosine of theta is approximately 0.19, and then so theta, taking the cosine inverse of 0.19 gives you 79.11. And no surprises here. Here is the two lines. The orange one is obviously D1 and the pink one is D2. And drum roll, please. 79.11 degrees. So pretty nifty stuff. Hopefully you found that useful. It's getting very heavy at the moment, but I think it's interesting stuff. If you found that at all useful, give us a thumbs up and subscribe. And so we can keep working through the specialist course and eventually working through the methods and the general maths course as well. So good luck with everything you're doing, and I'll talk to you soon.